Section 1.7 did an introduction to exponents, and in section 1.8 we're going to delve a lot deeper with exponents. And I'm going to make sure as we take a look at the properties of exponents, which comes first, that I justify for you why they work. Because if you get stuck on a test and you're not sure, am I supposed to add these or am I supposed to multiply these, having seen why they work might help to jog your memory in that kind of an environment. So we have seven different properties that we're going to take a look at for exponents. I'm just going to go one slide at a time. I'm going to write down what the property is and then justify them. So the first property says that a to the m times a to the n is a to the m plus n. That's property number one. The second property says that a to the m divided by a to the n is a to the m minus n. And the third property, while very similar looking to the first one, only has one base. It says a to the m, and then there's to the power n on the outside, and I multiply the m and the n. So these are our first three properties, and I want to show you with some examples why they work. So let's say, for instance, that we had a cubed times a squared. So as you've been working on properties of exponents back in section 1.7, we talked about a cubed meaning that it's 3a's multiplied, right? And a squared meaning it's 2a's multiplied like that. That's what it means. So if I were to consolidate these, so I've sort of, broken them all apart into their pieces, and if I were to merge them together and consolidate them back up, I would find that I have 5a's, so it's a to the fifth. And if you take a look at how those exponents happened, 3 and 2 became 5, very quickly you decide, oh, that was addition that did that, right? So if on a test or a quiz you were tempted to think, oh, this is that multiplication one, and you just did a simpler example like that, you should hopefully be able to remember that, no, that's the addition property for the exponents. Let's take a look at the second one. So we're going to do a to the fourth on top and a to the first on bottom. So a to the fourth means I have 4a's, and a to the first means I have 1a. And the things that we've been looking at in terms of fractions tell us that when I have lots of multiples of things on the top, right, like factors on top and a factor on bottom that reduce, I'm allowed to reduce them, right, cancel them, simplify them, whatever language it is you'd like to use. And what I notice when that happens is there's 3a's left over 1, so it's just 3a's, and that becomes a cubed. And again, how do I get from 4 and 1 to 3? Subtract, right? On the third one, I want to use an example quite similar to the first one. We're going to look at a cubed squared. So a cubed means I have 3a's. The square on the outside means I have the 3a's twice, right? So how many a's do I have? 6. And again, how do I get from 3 and 2 to 6? Multiply. Now, it's probably worth noting that you have to make sure that you choose your example kind of well, because if I had chosen, say, for instance, 2 and a 2 here, it would be hard to decide, did I multiply or did I add, right? So you can't just completely arbitrarily choose these numbers to see which property was that again. You have to be a little bit selective by choosing these numbers a little carefully to make sure you're getting the right property. On the next page, we've got 4 more properties. The first one is kind of like the counterpart to distribution of multiplication over addition or subtraction. And it looks like you distribute the exponent across the parentheses into the multiplication. So you have a to the m, b to the m. Number 5 is the exact same thing, but with division, a to the m over b to the m. Does anybody remember what number 6 is?
1.
It is 1, and I'm going to justify for you why, because it's the easiest one to actually prove. I didn't prove anything on this page. I just gave you some examples that kind of showed you why it works that way. I can actually prove this one very easily, number 6, to help you remember why that's true. And the last one tells you what to do with negative exponents. Negative exponents do reciprocals. So this becomes 1 over a to the n. So I do the reciprocal, or you can say I take the value and I move it into the denominator, makes the exponent positive, kind of whatever phrasing you'd like to think about it as. So again, let's kind of look at some examples as to why. So let's say I had AB cubed. So anytime I cube something, it means I multiply it by itself. So I have AB times AB times AB. That's what AB cubed means. And I have some really wonderful properties with whole numbers that don't always exist for other numbers, and they don't always exist for other operations, but they work for multiplication in whole numbers. And what they say I can do is that I say I can move numbers around as long as it's on multiplication. So those two properties are the associative property, right? We talked about that last time, what we group things with. And the commutative property, which has to do with switching the orders, right? 5 times 3 is 3 times 5. So because I'm allowed to regroup and I'm allowed to move the numbers between these parentheses and so forth, I can very much group the 3 A's together and group the 3 B's together to recognize that this is A cubed, B cubed. I know that's super tiny now, but I need to shift it a little bit. Is that okay? All right, let's do another one. Property number 5. So we're doing the same thing, but we have A divided by B, and we'll do it cubed as well. So again, this is A over B times A over B times A over B. This one's even easier because I don't physically have to shuffle anything. It's multiplication of fractions, so I can multiply straight across the top, straight across the bottom, and sure enough I have A cubed over B cubed. Okay, and those are not proofs because I've used arbitrary numbers in them. I've used 3, I've used 2, I used a 4, I used a 1. Once you take the general property out of something, you lose the ability to actually say that it's a proof. But I can do a proof on the last one, or the 6th one, excuse me, the next one, really nicely. So I'm going to write a to the 0 in a very odd looking for now way. I'm going to write it as a to the m minus m. And while it may look odd, does it at least look correct? Is it true? Yeah, it's true, right? M minus m is 0, no problem. So what we're going to actually do is we're going to use this property number 2 backwards. Property number 2 says that if I have the subtraction of exponents, if I move the other direction, because it's an equality, you can do that. It says that if I have subtraction of exponents, it's the same thing as having division with the bases being the same. So I can take my statement that looks like subtraction and I can rewrite it to look like division where the bases are the same. But what happens when you divide a number or a value by itself? Get 1. Yeah. And it works no matter what that number m was. Any number will work. Okay. Our last property, I can actually hinge upon the property that I just used, and I can actually do a proof for it as well. So if I have a to the negative n, a different way of writing this, again, you may not think that you would think to do it, and that's okay, is 0 minus n as the exponent. Is it at least true? Negative n is 0 minus n. It's okay. And I can separate it just like I did on the last problem's proof by writing them as division. And then I'm going to use what I learned in step 6, or rule 6, property 6, whatever, in property 7, and a to the 0 is in fact 1. So I have a 1 over a to the n. Okay, so we're going to do some examples, right? The examples that we're going to do, we're going to use the properties I'm not asking you to prove the properties over and over again. I proved them to you, or I justified them for you this time. That's fine. You don't need to justify them for me again. I did it so that hopefully if you forget something, you'll have a way to recreate it in that kind of a moment. But as we work with the problems that we're doing, we're just simply going to be applying the properties that we just discussed, properties 1 through 7. So for example, on number 1, you have x squared times x to the 5th times x to the 4th. So what property are we going to use?
Addition.
Yeah, the addition property for the exponents, right? It was the very first property. And I'm going to add the exponents together. So what is 2 plus 5 plus 4?
11.
It's 11. So this is x to the 11th. Right? I'm not going to write out x 5 times and x 4 times and x 2 times. That's not what I'm doing. I'm using the properties that I was given. Okay, so now on number 2, we have a bunch of y's to powers, but we happen to also have some coefficients. And I'm allowed to do regrouping, which I showed you in one of the justifications as well. But I can actually just take each of the coefficients and multiply them first. So what is negative 4 times negative 3?
12.
That's 12. I meant to do that. Okay. That's what I meant to do, 12. And then 12 times my negative 2 is negative 24. Okay? You don't necessarily have to show that, but just that's what we're doing. We've got negative 24. And then we have our y pieces. I have y squared, y cubed, and y. That is understood to be y to the first. And now I'm using the same property I used on the last example. And what will I do with those exponents? Yeah. You'll add them, so you get y to the 6th. No, you're fine, Haven. It's fine. Yeah, you'll add them, so you get y to the 6th. 3 is a little bit different. What's going on 3 that's a little bit different? There's 2 variables. What that means is that we can't combine the variables into a single variable because they're different. I mean, that's really what it means. All the numbers we can deal with just like we did in problem 2. So I can take 6 times 4 times 2 times 3. What is 6 times 4 times 2 times 3? Feel free to grab a calculator if you want to. Times 4 times 2 times 3.
144.
This is 144, yeah. So this is 144. And then I'll take the pieces that match, right? So, well, I'll just do y squared because it's first. So if I have y squared and I have y cubed, what will that become? Y to the 5th. That's right, good. And then on my x's, I have x to the 3rd, and I have x, which gives me x to the 4th. Sometimes we don't like the y's written before the x's because we're OCD and it's not alphabetical. So if that's you, because that's kind of me, feel free to switch the x and the y around. It doesn't make any difference. But it is 144 times the y to the 5th and the x to the 4th. Any questions so far? All right, we'll keep going. How about number 4? Yeah, we will multiply those 2 exponents together. So 2 times 4 is 8. And that's it, right? Now number 5 begins to look like things that we were seeing in the last section where we have powers with parentheses, right? Y'all saw some of that, asked some questions about that even at the beginning today. So this is a little bit messy. We need to make sure that we are in fact using that property, that we can anyway, use that property where it distributes like this, because the 3 as the exponent applies to both of the pieces inside. So we have 4 cubed, and I'll just write it that way first to remind us. And we have u cubed. So that's my property of exponents in play. But then I actually have to do 4 cubed because that's a numerical value. So what is 4 cubed?
66.
Yep, it's 64. So 64 u cubed is where that problem would end. Number 6 is just a little bit bigger version of number 5. So what do I need to do with the cube on the outside? Yeah, but I have to distribute it to all 3 pieces inside, right? So if arrows help you, arrows help me when I'm thinking about distribution to make sure I capture all of them, then use that. If it helps you to write it out, like maybe you just would rather write out this 3 times. You can do that. There's nothing wrong with that at all on a problem like that. So if it helps you to see it written that way first, then do that. It doesn't make any difference. Okay, that's what cubed means. If we do it as a distribution step, like we started on number 6, then we have 3 cubed. We have x cubed. And what will we do to the y squared? Yeah, it'll be y to the 6th. Good. So we multiply the exponents, right? It's an exponent to an exponent. It's property number 3 that we saw earlier. So we multiply the exponents. Almost done. What still do I lack? The 3 cubed. Y'all know what 3 cubed is?
27.
It is 27. So we have 27 x cubed y to the 6th. All right, number 7. So number 7 has another cubed, but there's something else going on here that we haven't seen before. 2 somethings, in fact. What do you notice? There's a fraction, so there's a fraction going on. That's one of the 2 things. What's the other thing going on that we haven't done with yet today? It's negative inside the fraction. Yeah, so as I'm sort of distributing this, which I can totally do, I need to make sure that the distribution actually applies to the negative as well as the 2, as well as the a, and as well as the b squared. It has to distribute to all those pieces. So we encountered this idea of multiple negatives in the last section. If I have 3 negatives multiplied, will I get a positive or a negative value?
Negative.
It will be negative. So my answer here is going to be negative. On the top, I have 2 cubed. I'll just write it as 2 cubed for now. If you want to write it automatically as 8, that's great. On the bottom, I have a cubed. And then I have that b squared cubed, which gives me 6. Yeah, multiply. Gives me a 6. Okay? So 2 cubed on top, a cubed on bottom, b6 on bottom. I do still need to write that, if you haven't already, as an 8 on top over my a cubed b to the 6th.
Why did you say it applied to the negative?
It applies to the sign of the problem. Remember what we were doing and seeing before when we were writing them out, which is really what we did last section, is we would write out the thing 3 times, like this, right? And when I have those 3 negatives, that's the negative being cubed.
Oh, that's good.
Yep. All right, number 8. So number 8, we actually could have done without properties of exponents. It actually reduces very nicely, but it shows up again in this section because it does actually have some of those commonalities. I can look at my numerical, like my coefficients, the numbers. I have 14 over 35. What do they have in common? They have a 7. So what is 14 divided by 7? It is 2. And what is 35 divided by 7? It's a 5. Now, we also happen to have an x on top and an x on bottom, right? Like exactly the same thing. So we are able to reduce that or simplify those to cancel those out. And I have a y left on bottom. So I have a 2 on top and a 5y on bottom. And that's reduced. It gets a little bit more complicated on number 9 with the fraction pieces that we have. On number 9, I have x squared y to the 6th over xy squared. There's lots of ways that we can do this. One of the ways that works really nicely is to use property number 2. So property number 2 says that if I have x with a power on top and I have x with a power on bottom, or I used a's, but whatever, I subtract my exponents. So I have x on top to the power of 2, and on the bottom is the power of 1, so it's x to the 2 minus 1. Y on top with the power of 6, the power of 2 on bottom, so it's 6 minus 2. So 2 minus 1 is 1, so you can either write x to the 1 or just x. 6 minus 2 is 4, so I have y to the 4th. Now, is that the only way to do the problem? No, it's not. If you want to reduce it by looking and saying, hey, look, let me do this differently. There's 2 of these, and it can cancel with 1 of those. There's 6 of these, and it can cancel with 2 of those, leaving me with 4. You can do that. It's totally fine. We're going to move into another problem here where it gets a little bit messier to do it that way, but this works just great for this problem, and you'll still get xy to the 4th. Number 10, I'd like to show you a different thing that happens on this one if I tried to do my exponents the way I just did them. So this was 1 minus 4, because it's 1 on top and 4 on bottom, and w to the 2 minus 6, because it's 2 on top and 6 on bottom. It's similar to the last problem, right? But what do you notice those exponents end up being? What is the first exponent? It's negative 3. And the second exponent? Negative 4. So I'd like for you to put yourself a note in here, highlight it, circle it in red, whatever you knew. Answers need only positive exponents. So this is a very good example of one where even though I used the properties, which is great and I did, I'm not done because I've got negative exponents. Negative exponents are not hard to sort of deal with. If they're an exponent that's negative, like these are, we're going to simply put them in the denominator. That's property 7. So I've got u cubed and w to the 4th in the denominator with the 1 on top. Now, interestingly enough, we'll get to it shortly, but if I have a negative exponent in the denominator, I can actually also pull it up to the numerator and make it positive. So that same property works in reverse, too. But at that point, my problem would be finished. What do you notice on number 11? It's to the 0. And what did we learn that anything to the 0 power was? 1. So everything here in blue is the number 1. This is really 3, negative 3, let me get that negative in there. Negative 3 times 1, or simply it's negative 3. Okay, so don't do a whole lot of work if you see powers of 0. It makes things become 1 very fast. I'd like to show you a cool way that you can handle fractions when they're raised to a negative power. So I mentioned a moment ago that if you have a negative power in the numerator, you can move it to the denominator, and a negative power in the denominator, you can move it to the numerator, right? And that's exactly what would happen if I distributed this negative power through, right? Negative powers on everything. So when I have a fraction raised to a negative power, I can actually just do the reciprocal and make it to the positive power. So the reciprocal would be 3 over 2u raised to the power 2. And that's probably your easiest way to get rid of that negative, because that's what it was, right? That's what property 7 said. U to the negative, was it negative 1? I think it was negative 1. A to the negative 1, whatever letters I used, makes it 1 over a. So it's the same thing here. Now we can distribute the power in to all 3 of the pieces. So I have, again, you don't have to write it as 3 squared. You can just do it. But I do have each piece individually squared, and I want to remember that. So 3 squared is 9, 2 squared is 4, and u squared is u squared. So this is 9 over 4u squared. All right, so what are we going to do on number 14? Oops, did I skip 13? Was on the page? Oh, it was, there it was, sorry. What are we going to do on number 13? Yes, we're going to add those exponents. So what is negative 3 plus negative 6? Negative 9, you're right. But it's a negative exponent.
1 over x to the 9. 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 1 over x to the 9
Yeah. 1 over x to the 9th. Okay, any questions on that so far? Okay. 14, kind of similar. Y to the negative 1 times y to the negative 5 times y to the 4th. So I need to take negative 1 plus negative 5 plus 4. It's negative 2, you're right. Y to the negative 2, which is what? Right, 1 over y squared. All right, our last example has a negative exponent. So I still suggest, let's flip it to get the exponent to be positive. And the reason I suggest that is because on this one especially, I'm going to have negatives inside. There's a lot of negatives going on. And I would like to eliminate a negative as quickly as I can. And the quickest way to eliminate it is to make something reciprocal. So I can take this and I can rewrite it as x to the negative 2 on top, because that's what's on bottom, and y. And then xy squared on bottom. And all of this is raised to the power negative 3. Now you have a couple of options. Oh, not negative 3, positive 3 now. Yes, thank you. You have a couple options. If you want to pull the 3 in and sort of distribute that through at this point, you could do that. But you also have inside of there a fraction that can be reduced, right? You've got x's on top, x's on bottom, y's on top, y's on bottom. So I tend to reduce things instead of making them bigger. And we did that with multiplication of fractions, right? Where we can multiply across the top, multiply across the bottom. I said, or we can reduce across diagonals and keep things smaller. Keeping things smaller is usually easier to work with. So I would suggest at this point we consolidate the fact that we have x's on top and x's on bottom. And I have on top x to the negative 2 minus the one on bottom, which is negative 1, right? Subtract the 1 that's there. And then I have a y, and on top it's a 1, and on bottom it is 2, so it's 1 minus 2. I still have it to the power of 3, but I'm not going to deal with the power of 3 just yet. So inside here I have negative 2 minus 1, which is negative 3. I have 1 minus 2, negative 1, yep. And I have a 3. And you notice I have negative exponents inside. I can either distribute now, or I can deal with the negative exponents now. It doesn't make any difference. At this point, it's the exact same operations, just reverse order. So if you want to distribute the 3 now, feel free to. I'm going to deal with the negatives now. And so the way that we deal with the negatives, my office screen, I am. Let me do it over here then. The way I deal with my negatives is that they go into the denominator, right? So I have x cubed in the denominator, and I have y to the 1 in the denominator, to the power 3. Okay, is that all right? Then you can distribute. And you could have distributed before. There's options, I guess. There's several ways that you can do this. On top, 1 cubed is 1. So that one actually doesn't change. What is x cubed cubed? Is it to the 6th or is it to the 9th? It's 9. So remember, when we are doing a power to a power, we multiply the powers. It's when the bases match that we add the powers. So this one ends up being x to the 9th. And then I have y to the 1st to the 3rd. So multiply them and I get y to the 3rd as well. Now, it's worth noting that if I did it in a different order, I'd get the same answer, right? It doesn't matter what order I do them in.